Hello, everyone. My name is Erik, and I'm one of the GC guys in the Java platform group at Oracle. And today I'm going to talk about generational ZGC. Oh, can you hear me? It's always a bonus. So I'm going to talk about generational ZGC, and then I'm going to talk a little bit about what's coming next as well. So ZGC is a low latency garbage collector, and the main thing is that it's running concurrent to the application and without inflicting any long GC pauses. So the goal of the project has been to scale up to terabyte size heap while maintaining low latency, so a millisecond, and something that we also take very seriously is that we want to do this without excessive user configuration. So there's a lot of effort that has gone into automatically tuning the GC. So this all sounds great. There has, however, been one annoying problem, and it has to do with the very concurrent nature of the garbage collector. As you can imagine, when we start doing concurrent GC, there is a certain amount of memory left in the system, and the application is running concurrent to the GC at a particular allocation rate. So we can end up in a situation where the application is allocating memory faster than the GC can keep up with. And what happens then is something that we call an allocation stall. It might look something like this in the GC log. What happens then is that while the garbage collector is running, the application is allocating just too fast, and we end up exhausting the heap before the GC has a chance to reclaim memory. And then the application has to sit tight and wait until the GC can catch up and reclaim memory. So there are some ways of getting around this, such as setting a larger heap size. It essentially gives the GC more time before it runs out of memory. There are some other things you can do, like increasing the number of GC threads to make the GC run faster, but it's a little bit of a slippery slope, because if you start adding too many GC threads, then you'll start preempting the application threads, and that's not gonna look very good. So in some workloads, particularly if you have large object graphs and large allocation rates, it's going to be a bit nasty. So what would be really nice if we could somehow find a way of reclaiming memory faster. And that is indeed what we've spent the last couple of years figuring out with JEP 439 generational ZGC. This is a new feature available in JDK 21. You can turn it on with the use ZGC Z generational flags. You should try it out. So the main thing is that we are exploiting the generational hypothesis, which is a pretty common pattern in Java programs, that most objects tend to have a short lifetime, which means that they typically die young. So what a generational collector tries to do is to split the heap into two logical parts, a young generation and an old generation. When you allocate an object, it first gets allocating in the young generation, and only after it's survived a number of young generation collections, it gets ready to get promoted to the old generation. Most of the objects won't get promoted to the old generation, and therefore reclaiming memory in the young generation is significantly more profitable. So what this buys us is the ability to withstand higher allocation rates while using less memory and less CPU. Now, I mentioned that we have this split between a young generation and an old generation, but in the memory layout, we have a discontiguous heap based on regions. So it looks a bit more like this, that we have a bunch of regions, and each region can be young or old, and then you have some free memory in the cracks between. So if we look at the phases of the generational ZGC when we're collecting a generation, it might look something like this. So we have some vertical blue arrows here that denote GC pauses, and some light blue horizontal arrows here that are concurrent phases. Starting at the beginning, we have a mark start pause, and this is a synchronization point. It doesn't really do anything. That just denotes now marking has started. Then we start running the application and do some concurrent marking. And while we're doing a concurrent marking, we're also doing lazy remapping on objects that moved around the last GC cycle. At the end of this, we do mark end pause, and this is a synchronization point where marking terminates, and this is essentially where stuff dies. Then we start running again, and we have a preparation phase before evacuation can start. But here we also have some generation-specific stuff like reference processing and class unloading that is running concurrent to the application. And after all this, we have a relocate start pause. Again, a synchronization point doesn't do anything. It is the mark that now we're going to start moving objects around. And when we start running, that's indeed what we do. In the concurrent relocation phase, we move objects around so we can free contiguous memory. Now, something that's new with generational ZGC is that the young and old generations, they're running concurrent to each other and concurrent to the application. So this is a very concurrent system, which is very interesting. The way that we package these collections up is through something we call minor and major collections. And this is what you're going to end up seeing in the GC logs. A minor collection collects the young generation only. And the way we do this is by finding the roots to the young generation, which now includes a remember set data structure that tracks the fields of objects in the old generation that potentially point into the young generation. We trace through all of these roots, the transitive closure, and figure out what's live in the young generation. Once we know that, we can start moving objects around and free up memory. Major collections, they want to collect the entire heap, the young and old generations. So the way we do this is by starting with the young generation. And it works similar to a minor collection. We start with the roots, trace through the young generation, but while we're tracing through the young generation, we find the roots in the young generation that point into the old generation. And this way, when the young generation has finished, we can trace through all the live objects in the old generation. And once we computed all the live objects, we can start moving objects around and reclaim memory. So something that I mentioned is very important to us is automatic tuning. And this is something that we kind of designed for from the beginning. Especially now we come with a generational GC, it usually comes with a bunch of interesting numbers and options that you have to figure out as a user. We don't want that. We want it to be our problem that we choose generations. So the first thing is how large should the young generation be? And this can be a pretty tricky problem to answer, and it's something you don't have to answer with generations ZGC. In fact, the XMN option usually used to size the young generation. It doesn't do anything. It doesn't have a meaning in generational ZGC. There is no concept of generations having a capacity. Instead, you can ask at a given point in time how much memory is in the young or old generation, but the pool of free memory is not coupled to any generation. So this has been pretty tricky to get right, and essentially boils down to a bunch of tricks. Like we have colored pointers that allow us to distinguish two pointers with the same address and see that they're actually different, and that allows us to use memory reclaimed during GC as 2-space memory to reclaim even more memory. So with only a small bit of memory, we can move all the objects around that we need to. And then you're thinking, what if you don't have that small amount of memory? Well, then we have even then a fallback solution where we can do in-place compaction within a region. And this means that we never have evacuation failures in ZGC. This is something that we worked pretty hard for, but the engine and the result of the whole thing is that you don't need to set this flag. Another interesting question is, what should the tenuring threshold be? The tenuring threshold denotes how many young generation collections we wait until we decide that an object is ripe to go to the old generation. And it can be really tricky to find out a good number for this. And it might even be that the application goes through multiple different phases where in some phases you want one number, in other phases you want a different number. It's just very hard to get right. So we have a whole bunch of interesting calculations that figure all this out automatically. And we can do a pretty good job at this, I think, in particular because we did have live analysis before we start moving objects, unlike most collectors. That means that when we are trying to pick this number for a collection, we know the consequences. Whatever number we pick, we know exactly how many bytes are going to move to the old generation, which is pretty cool. Another interesting question is, when should we start an old generation collection? Well, it depends. It's a fairly complicated cost model. The easy answer might have been to have a JVM flag where we just have some initiating heap occupancy % or something, and say, well, if the heap goes over this limit, then it's time to do old generation collection. But again, it can depend on what application phase we're in, and it's just very hard to get this right. So what we've done instead is to do that cost modeling, so we can automatically compute this number. Another tricky thing is, how many threads should we be using when we are running GC? If you pick too few, you get an allocation stall, not very good. But if you pick too many threads, then you might start preempting the application, and that's not very good either. And to some extent, we had support for this in the normal ZGC, where when we start a collection, we could figure out how many threads we think we're going to need. As it turns out, though, while we're doing the GC, the allocation rate can start spiking unexpectedly. So we're taking this one step further in generational ZGC, and now we can change this number while the GC is running and start boosting the GC threads should we need to accommodate spiking allocation rates. So I talked a lot about what you don't need to set, so then you might be wondering, what should I set then? And I think the best advice is to set the max heap size. Now, since this is JVM-LS, I should probably talk a bit about how this works under the hood as well. And to do that, we have to first look at colored pointers in ZGC. This is a very, very crucial core design element of the GC. And what we call colors are metadata bits in the pointers that encode some extra life cycle information. And the way this works in normal ZGC is that we have some high order bits that use multi-mapped memory. So each physical page is mapped multiple times in virtual memory, which allows us to refer to the same object with different colors. This has been great to build good load barriers. So load barriers are the instructions that we emit when we load a reference from the heap typically. And what it does is to check if these colors look good or bad. If they look bad, we take a slow path and fix the colors and do some operation. Something to keep in mind is that a typical distribution between loads and stores is approximately 80% loads and 20% stores in terms of barriers anyway. So it's been pretty good that we've been able to have a 2-instruction load barrier with this multi-map memory trick. Now with generational ZGC, we have an extra generation, it's running at the same time, so they have completely different life cycles. So we end up needing a whole bunch of more colors. And in fact, we ended up in a design where we need 12 different color bits. And as you can imagine, multi-mapping memory that many times is starting to get a little bit painful. So what do? We had to invent something new. And we call that solution Colorless Roots. The idea is that only the in-memory representation of pointers have colors. When we load a reference from the heap, as part of the load barrier, we remove the colors and end up with a colorless root. It's just an address. Instead, these colors are restored as part of a store when we store a reference back into the heap. And this way, we don't need any multi-map memory anymore. But the main challenge has been, how can we perform this extra operation of removing the colors as well without a cost? We don't want to have more than 2 instructions. In order to understand that, we have to look at the layout that we have chosen in the end for colored pointers in generational ZGC. As you can see here, we have a whole bunch of metadata bits in the low order bits instead. And 4 of these colors are relevant to load barriers. These are the dark blue with a capital R colors. If a pointer is null, then they're going to be all zeros. Otherwise, we expect that if we find a good pointer, it's going to be exactly one of these bits set to 1. The rest are going to be 0. So that's what we want to look out for in a load barrier. And then we want to uncolor it, so we end up with the following colorless pointer layout after the load barrier. As you can probably imagine, the instruction that gets us from the previous representation to this is going to be shift right. So if you look at the assembly for the x86-64, that is indeed the case. So on the right-hand side, we see the load barrier for generational ZGC. It's a shift right instruction, and the immediate value there says how many bits should we shift right, and we pick a value that corresponds to the index of the bit that we expect to be set to 1, so the good bit. The result after this shift should be an address. And then you see this jump if above instruction. You're wondering, well, what do you mean above? So it turns out that we have some interesting side effects in the shift instruction. The carry flag is set to the last bit that we removed, which, remember, if it was a good pointer, should be a 1. And if it's null, it should be that this 0 flag is set. So this is the very definition of the jump if above instruction, that we will take the slow path if the carry flag is 0 and this 0 flag is 0. So this way, this perfectly captures the condition for a bad pointer. So we're essentially using the side effects of the shift right instruction to also produce a condition code that we can branch on. And this way, we could get away with having a load barrier that's 2 instructions that does more. And on the left-hand side, you see that we also had 2 instructions there, and we still have 2 instructions. It's worth noticing that the index we're shifting depends on the GC phase. So the way we deal with this is we have cross-modifying code that patches these immediates when you change the GC phase. There's a whole thing around that. So as you can imagine, since we have different shift indices or shift amounts, we're going to end up with addresses that have slightly different layout depending on which GC phase we're in. So as we can see in this picture, depending on which one of these bits are set in the remap bits, the dark blue ones, we have addresses starting at different indices. As it turns out, though, the part of the address that starts intersecting with the colors are up to exactly 3 low-order address bits. And since the minimum object alignment in 64-bit VMs is 8 bytes, that means that these low-order bits in the address are always going to be 0. So the fact that they intersect doesn't matter. Please, Roman, don't change this stuff. So this was not obvious at all, and it took us about 10 different Barry models before this one until we ended up with this. So the benefits we end up with is that we now have a larger addressable heap than ever, and we can at the same time have more colors than ever. And the problem that we used to have with multi-map memory is that people will come saying, look at my RSS, it seems like we're using 3 times as much memory when we're using ZGC. And we'd say, well, you should probably look at the PSS value, and people don't know what PSS is, and few tools support it. So it's been an uphill battle that we don't have to deal with anymore. And we still end up with a 2 instruction load barrier, even though it does more work. So should talk about store barriers. This is the machine code we emit when we store references typically into the heap. The main design principle with our store barrier has been to detect the first store of a field after we change the GC phase. And then we want to take some action and color the pointer. As it turns out, most of the important things happen at the first store, and the rest don't matter. The way that we detect that is through color tricks. And as you see in this picture, we have these 12 colors in total. They're all relevant to the store barrier, unlike the load barrier. So when we have detected this is the first store, we take some action. And in both the young and old generation, we're using Snapshot at the beginning marking. And in Snapshot at the beginning marking, you're starting with a snapshot of the heap. And that's what we're going to trace through. And as you can imagine, when you start breaking these links, when you start running, it's only really the first store that breaks fields from this snapshot. Most GCs can't detect this, so they end up in queuing all the time. But we can detect that this was the first store, and that's the only time we need to do anything. And a nice synergy is that it's the same with remember set maintenance, that it is, again, only the first store that matters. Because once you have inserted your field into a remember set, you don't need to insert it again on the next store. So this all worked out pretty nicely with nice synergies. Speaking of remember sets, in generational ZGC, we have 2 remember sets. The guiding principle there is that we have an immutable one that we call the previous bitmap, so it's implemented through bitmaps, and it's precise. The previous one is immutable while the GC is scanning it, so it doesn't need to worry about interactions with the program. The application is inserting entries into a different remember set called the current one, and these 2 flip when we start marking. So the cost is 3% memory, and the nice thing with this is that we don't have any fencing around the store barrier, which you can typically end up having if you have concurrent clearing and scanning of remember sets. So in terms of instruction sequences, we can see on the left-hand side that with normal ZGC, well, we didn't need any store barriers because we didn't have any generations. Now we have generations. On the right-hand side, we see we do have a store barrier. First two instructions, a conditional branch to essentially find out, is this the first store? Followed by a shift and or sequence to essentially color the pointer. And there's some immediates in there, and they are updated with cross-modifying code, which is a whole thing on its own. So you're thinking that this sounds pretty good. What's the performance? And of course, when you have a generational collector, the benefit comes from a combination of old objects and higher allocation rates. So it depends on your use case. But one data point is that we ran Cassandra 4 with a 128 gigabyte heap. We started running with ZGC until you get allocation stalls. And at the same injection rate, we went over to generational ZGC and saw how much higher injection rate can we start running until we run into issues. Turns out that we can run about 4 times the injection rate. Looking at the memory side, turns out that with generational ZGC, we can actually reduce the memory size of the heap with 75% less. So ended up in a situation where we get 4 times the throughput and with 75% less memory, while of course retaining the sub-millisecond GC pause times. So this has been pretty cool, and we feel pretty happy about it. And now GC is finally done, and I can go to some sunny beach somewhere and just relax. No, that's not what's going to happen. There is one more thing. So the next thing we're going to work on and investigate is thread local GC, which I've been thinking about for quite a while now. The idea with thread local GC is to figure out what objects are reachable only from the current thread. As it turns out, there's typically a lot of data reachable only from the current thread. And we want to collect this garbage more efficiently and potentially be a bit nicer to the CPU caches as well. Why do this now? Well, as it turns out, we have a bunch of interesting synergies with other projects. One of them is Project Loom. And I think that we're going to have more local data than ever with Project Loom. Because if you think about your asynchronous code that takes your data and scatters it over some fork join pools, it's going to be tricky to find that this was somehow private, because it's not. Whereas if you take the same trivially synchronous virtual thread code, you can find out that actually this stuff is all local to the thread, semantically speaking. So another interesting problem is, when do we choose to do GC? And that can be hard to know with a thread local GC design, but we have a fairly intuitive point with virtual threads that when the virtual thread terminates, that might be a good time to do it. Why? Well, partially because when a virtual thread terminates, it has 0 stack frames. That means that there are no roots. And most of the GC overhead typically comes from tracing live objects from roots and doing something with them. Well, that now becomes a no-op and we don't need to do anything. And on top of this, as it turns out, that these stack chunk objects that Ron was talking about earlier, that stores the stack, well, they are thread local by definition. So even if it turns out that the entire application is all shared objects, there's nothing local at all, you're still going to be a win. So it's pretty hard to lose. So if you think about the case of a global GC, look at these horizontal light blue arrows as platform threads executing. Inside of them, we have dark blue arrows representing virtual threads running on these platform threads. Wherever we stop the world to do a GC, there's stuff going on. Everyone's up to something, and that means there are routes, and we need to trace through them and do things. Now, in a thread local GC world, the situation is going to look like this instead. We can intersect when the virtual threads finish, and then they're not up to anything, there are no routes, and we can just reclaim all the garbage. Another interesting synergies with Project Leiden. The reason for this is that we're now getting some good infrastructure for warm-up problems. And as it turns out, finding the boundaries between private and shared objects is something that you can define as a warm-up problem, which is my intention. Essentially, we train the boundaries between shared and private objects, learn from mistakes, and then you can do this learning before deployment, serialize it, and when you start running at deployment time, well, we'll already know the boundaries. Some important design goals. The most important, probably, is to not lose what we have. So in the worst case scenario, we still want to retain the low latencies we have, the scalability, ease of use, as well as the performance that we fought pretty hard for. We also want it to be completely automatic. We don't want no annotations, what's local and what's shared. Please just fill it in here and cause trouble. And in fact, I think that the JVM can do this annotation better automatically than a user ever can, because we can look at not just allocation side, but the context of the allocation side, who call this stuff transitively, and make better decisions. So the general idea is that I'm going to speculate their private objects. They live in something called a private heap, and we detect violations to the speculation, learn from our mistakes, and lazily heal the system. And we also want to avoid pathological costs when the violations are detected. Some other possible designs would be to do some expensive unbounded tracing when you have violations at the point of a store. We're not going to do that. Instead, we're going to fall back to the previous behavior and just do whatever we used to do. It wasn't all that bad anyway, right? And continue training until the system has learned and healed. And eventually, this system will hopefully stabilize, and that stabilized state can hopefully be captured in some Leiden artifact. More details about that we can have in an upcoming workshop. And yes, that's it. Thank you very much.